Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 1, Part 3, and we are on 1.1, What Chemistry is About, and today we're going to learn about significant figures. So, a significant figure tells us how precise a measurement is. So, in math, if you were to put these numbers into your calculator, they would all be the same. It would just cut them off to 50. In science, they are not the same. So we know this from rounding. This measurement could have been somewhere between 46 and 54 centimeters. So that could be, it's quite a bit of difference. Whereas this one we know cannot be 47 centimeters, couldn't have been rounded up from 47 centimeters. We know it to the nearest tenth. Whereas this one we know to the nearest hundredth of a centimeter. So it could have been like 49.95 and was rounded up. And this one we know is exactly 50. It's not 47. It would be 50, and that's why we have the decimal point. So these numbers are different in science, and the significant figures tell us how those measurements are different and how precise our measurements are. What else? So significant figures, and please do write all of this down. Significant figures in measuring include all known digits plus one that is estimated. When you're measuring mass, give all the digits that show up on the scale. All of those are considered significant. So for example, if we were to read something on the scale, we know that our balances go to the hundredth of a gram. So all four of these digits are considered significant and known digits. So if you notice on our balances, when you're measuring something out, sometimes that last number will flip back and forth and it could be kind of frustrating. Well, that is because the accuracy, the precision of the balance is the hundredth of a gram. So is about 1 or 2 hundredths of a gram. So that last number, that hundredth of a gram place, is actually estimated. But all the other ones, the tenths place, the ones place, and then the tens place, would all be known digits. So I'm going to get a underliner, and we know that these three are known digits, and then the estimated digit is this last one right there. So in measuring, you include all known digits plus one that is estimated. So all known digits plus one that is estimated, and that gives you your significant figures when you are measuring. So we were talking about mass. What about length or volume? Well, to find the correct number of significant digits when you are measuring length or measuring volume is you report all known digits plus one more digit, which is an estimate between the smallest subdivision. So what does that mean? Well, let's look on page 15. Looking on page 15, this picture shows a graduated cylinder, water being measured in a graduated cylinder. And so let's figure out the value of the subdivision. Well, we know we go from 15 to 20 milliliters, and there are 1, 2, 3, 4, 5. So the difference between 20 and 15 is 5, and 5 divided by 5 is 1. So this is easy. Each little division is 1 milliliter. But we just talked about when we do significant digits, we have to do one more place. So one place more exact than the ones digit is the tenths digit. So our answer is going to have to be estimated in the tenths, excuse me. So we know that the water's up here, so that's 15, 16, 17, 18, but we can't just say 18, it has to go to the ones digit. And we always look at the bottom of the meniscus. And if you can see, the bottom of the meniscus is right there on the line. So I would actually write 18.0 milliliters as the correct measurement for that volume. To review, when we're measuring length or volume to get the correct number of significant digits, we do one digit more than all known digits, and that's an estimate between the smallest subdivisions. So, what? We need to keep track of significant figures when measurements are used in calculations because we don't want to mislead someone about how precise our numbers are. Looking at an example, and you don't have to write this example down, you do need to pay attention though. If I measure the length to the 100th of a meter, and I measure the width to the 100th of a meter, and I calculate out those numbers in math, my number would be 0.1515 meters squared. However, that's not an appropriate answer in science because I am lying to people about how precise my numbers are. So I know to the hundredths of a digit, I know to the hundredths of a meter here and the hundredths of a meter here, and I'm telling people that I know to the like 10,000th of a square meter, and I don't. I don't know a number that's that precise. So we don't want to lie to people in chemistry. If you've watched the significant figures one with Hank Green, you will know what we do to chemistry and what he does to liars in chemistry. It's not that severe, but I do need you to know your significant figures. So our answers cannot have more significant digits than our measurements. So to make sure we're not lying to people, there are some rules to follow. So are you ready? Please write these down. Number 1, all non-zero digits are significant. So 438, none of these are zeros, so they're all non-zero. So that means that it has 3 non-zero digits. I'd like you to guess 26.42 and 1.7, and do make sure to put all of these in your notebook. For 26.42, if you said all of them were significant, you would be right. That's 4. 1, 2, 3, 4. And if you said for 1.7, all of them are significant, 1, 2, you would be correct. Good job. So looking at our second rule, the zeros, this is where they come in. The zeros get tricky. All zeros between non-zero digits are significant. So you get to count the zero that is between the non-zero numbers. So 5 and 6 are non-zero, so you get to count this 0. So we get 3 in here. All right, I would like you to take a moment and take guesses on 10,050 and 90 and 43 hundredths. Okay, this was a tough one. So 1 counts, and these are in between non-zero digits, so they count 1, 2, 3, 4. But this last one doesn't count, and we'll talk about why it doesn't count next. So this one only has 4. And then these 2 zeros count as significant. So it's 1, 2, 3, 4, 5. Oof, that 5's a little bit rough. All right, so let's look at rule number 3. Zeros at the end to the right of a decimal point are significant. So please write that down, and then let's go over 8.0. So zeros at the end to the right of a decimal point are significant. So this one, following the rule, is 2, because the 8 and then this 0 both count as significant figures. And why is that? Well, if this wasn't significant, we wouldn't have written it, right? It would have just been 8. So if we include it after the decimal point, then that's important. So take a moment and figure out the next 2. So if you said 4 for this one, you would be correct. 1, 2, 3, and then 4, because it's at the end to the right of the decimal point. And then if you said 1, 2, 3, 4, 5 for this one, you would be correct because all these zeros are at the end to the right of a decimal point. Rule number 4, leading zeros are not significant. So leading zeros are zeros before a non-zero digit. And these zeros are just placeholders, and they don't get to count as significant figures or significant digits. So in this one, 6 is my first non-zero digit, so all these are leading, so I only have one significant figure. So take a minute and write those down, your guesses. And this one, these don't count, only the 4 and the 7, so I have 2 significant figures. And on this one, none of these count, only the 8 does, so I have 1. Rule number 5. Zeros at the end of a number without a decimal point are not significant. If they are significant, put a decimal point to show this or put your number in scientific notation. So take a minute to write that down, and then let's look at this one. 4,830. Well, 1, 2, 3 get to count, but then the 0 is always the hard one. So this 0 is at the end of a number and there's no decimal point, so it does not count. So I only have 3 significant figures here. And why is this? Well, this could be a number that has been estimated. So it could have been 4,825 or 4,834. With that 0 there, we don't know if it's been rounded. So take a moment and guess how many significant figures these have. So for this one, if you said 1, you would be correct. The 6 counts. This 0 does not. It's at the end and there's no decimal point. And then if you said 4 for this one, you would be correct. If you notice, the difference is that there is this decimal point. We are saying that 0 is significant, it hasn't been rounded, it's not a placeholder. Okay, looking at rule number 6. When multiplying and dividing significant figures, the answer can only have the number of significant figures as the number with the fewest significant figures. So our answer is only as good as our weakest link, as our least precise number. So let's go through an example. So please write that down, and then let's talk about this question. So the mass is 1.5 grams, the volume is 4 milliliters, and our density is question mark. Well, we know that our mass is 1.5 grams. We know that our volume is 4 milliliters, and we know the thing that we're trying to figure out is density. So we also know that there's an equation for that, D equals m over v. So we're going to write down our equation and sub in our numbers and solve, and then we'll talk about what our answer should be in significant figures after we've gotten our answer, our math answer. So take a moment and write down the equation, D equals m over v, and then we're going to substitute in our numbers. D is our variable, so we'll write that. M is 1.5 grams over volume, which is 4 milliliters. And then we're going to get out our calculator and do the math. 1.5 divided by 4 equals 0.375. 0.375 grams per milliliter. Oops. Grams per milliliter. That is not our final answer, though. That's our math answer, not our science answer. And we're going to get the final answer in our next video. So a little bit of a cliffhanger. I will see you then.